Welcome back. This is part D of part D video for section 11.8 concept video. We will try one more example to find the radius of convergence and interval of convergence of the series sigma negative 3 to the power n x to the power n divided by square root of n plus 1. So here we are definitely going to apply the ratio test. So a sub n is negative 3 to the power n times x to the power n divided by square root of n plus 1. A sub n plus 1 is negative 3 to the power n x to the power n plus 1. This will be n plus 1, this will be n plus 2, then this will be n plus 2. So if you take the ratio an plus 1 over an, we will have negative 3 to the power n plus 1, x to the power, this will be n plus 1. So negative 3 to the power n plus 1, x to the power n plus 1 divided by square root of n plus 2. Then you are dividing by this an. So you are going to take the reciprocal and multiply. Square root of n plus 1 divided by negative 3 to the power n x to the power n. So if you simplify the ratio an plus 1 over an and then you take the absolute value, then you'd get absolute of, so here you notice the negative 3 to the power n can be crossed out with this one that gives just a negative 3. Then these things can also be simplified, x to the power n, and that will be an x. So this whole thing will reduce to negative 3x times square root of n plus 1 over n plus 2. As we are going to apply the limit, so it's we can actually divide by n, the numerator and the denominator. So this will be absolute 3x, absolute 3 times x, times square root of 1 plus 1 over n divided by 1 plus 2 over n. So this limit as n approaching infinity of absolute an plus 1 over an would become, when you take the limit of all of this 1 over n and 2 over n will tend to 0. So it is just 3 times absolute x as n approaching infinity. So this is the limit for the ratio test. So we know that the given series converges. This implies that the given series converges when this limit is less than 1, when 3 times absolute x is less than 1, or absolute x is less than 1/3, or when x lies between negative 1/3 and positive 1/3. And when absolute x is more than 1/3, it's definitely divergent. We also notice that when absolute x is more than 1/3, the series diverges. So the test becomes inconclusive when this limit is equal to 1. So we have to consider the end cases. So step 2, verify the convergence at the endpoints of the interval. The test is inconclusive when it becomes when 3 times absolute x equal to 1. That means x equal to plus 1/3 or negative 1/3. So those points need to be verified. At the end point, say x equal to negative 1/3 and x equal to positive 1/3. These are the endpoints of this interval. So let's try first x equal to negative 1/3. So substitute x equal to negative 1/3 into the given series. Into the given series. So we get sigma an would be sigma negative 3 to the power n. Then we have x to the power n. Then x must be replaced by negative 1/3 divided by square root of n plus 1. This turns out negative 3 to the power n, negative 3 to the power n will cancel out. So it becomes just 1 over square root of n plus 1. So what type of series is that? Is it convergent or divergent? It looks like a p-series with p equal to 1/2. So we can use limit comparison test. So choose sigma bn, which is equal to 1 over square root of n, which is n to the power half. So it's the p series with p equal to, so p series with p equal to 1/2, which is less than 1. Therefore, it is divergent. So we are going to compare it to a divergent series. So let's consider an over bn for limit comparison. So an is 1 over square root of n plus 1, which is this one here. Then we are going to divide that by bn, which is 1 over square root of n. So which means you get 1 over square root of n plus 1 over square root of n over 1. If you flip and multiply, it's n over n plus 1. If you divide the numerator and the denominator by n, you will get 1 over 1 plus 1 over n, which is equal to 1 as n approaching infinity. So if you do limit as n approaching infinity, an over bn equal to finite positive. As sigma bn diverges, sigma an also diverges. So sigma an diverges by limit comparison test. What it means is at x equal to negative 1/3, the series diverges. So now let's try the next endpoint, which is x equal to 1/3. Substitute x equal to 1/3 now. So the series sigma an would become sigma negative 3 to the power n, 1/3 to the power n, divided by square root of n plus 1. Now it becomes an alternating series, negative 1 to the power n divided by square root of n plus 1. Now you would apply the alternating series test. Which means you have to establish condition 1 and condition 2. condition 1 is the decreasing condition. So you notice that n plus 1 is more than n. This implies 1 over square root of n plus 1 is less than 1 over square root of n, which implies bn plus 1 less than or equal to bn for all n. Then we can prove condition 2, that is limit as n approaching infinity of bn is limit as n approaching infinity of 1 over square root of n plus 1, which is equal to 0 clearly. So by alternating series test, so continuation here. So by alternating series test, sigma an converges, sigma an is the given one, converges at x equal to 1/3. So in summary, the last step, so we have proved that the series converges when x lies between -1/3 and +1/3, and it diverges when x equal to -1/3, and also when x is more than 1/3 or less than -1/3, but it converges at x equal to 1/3. So the question is asking, what is the radius of convergence? So keep in mind, anytime the question is about radius of convergence or interval of convergence, you have to go with the ratio test first. To answer the radius of convergence part, we have to look at this step. So absolute x minus 0 is less than 1/3. So the radius of convergence is 1/3 or equal to 1/3. What is the interval of convergence? So it converges on the interval -1/3 to +1/3, but diverges at -1/3, but converges at 1/3. So it is open -1/3, closed 1/3. That is in this interval, -1/3 to +1/3, +1/3 inclusive, the series converges. So again, keep in mind, whenever the question asks you about radius of convergence or interval of convergence, you will go with the ratio test. First, you will decide what the radius of convergence is, which is the first part. Then you will look at the interval, then verify the convergence also at the endpoints of the interval. Also at the endpoints of the interval. Sometimes it will converge at both endpoints. Sometimes it will not converge at both endpoints. Sometimes it will converge at one of the endpoints. I would like the class to try this example 5 as a practice. Then also I have done in the section videos, I have done the suggested problems, some of the suggested problems. The problems that I have done in the section video are problem number 9. This problem is done. Problem number 9. Problem number 15 is done. And also 17. And these problems are done. These are for your extra practice. Some of them you can find them in the homework exercise as well. Hope these videos help.